Okay, so, I've got some homework back for you. Also, some people had some questions. There's actually a quite common question on this next machine language program. The exercise or the problem asks for you to write a program to add 3 numbers. So you must use the add instruction, and one of those numbers was negative. I think it was like a -3. So to do that, you need to store -3. Of course, in order to do that, you're going to have to figure out how to represent -3 in binary and then use the hexadecimal abbreviation for that so that you can load it. So that when the program gets and the data gets loaded, the -3 gets loaded. So I want you to use the add instruction. Don't use the subtract instruction. So yeah, you'll have to, but it should be easy. Yeah, right. Okay.
It's actually easier though than doing the subtract and negating.
Yeah. So what you should do is you should load and then add and then convert and then store and then output. Right. But then, depending on how many instructions there are, you got to figure out what the addresses of where those things are going to go. You know. Okay. Any more questions about the homework? And then was there an exercise as well?
Yes.
And some of you figured out that what you can do for the exercise. So let me give you a warning here. By now, people have figured out that whenever I ask in the exercise, what is the output of this machine language program, you can always just put those hexadecimal characters in the PEP8 simulator and run it and not even think about it. But of course, if you do that, you will be hurting yourself in the long run, because on an exam, when I ask you the output of a machine language program, you won't have that luxury of having access to the PEP8 virtual machine. So I recommend that you just do that to check the answer after you have figured out how to do it. Okay?
I was under the impression you were literally asking us to put it in. Okay.
No, the whole idea is for you to be able to decode machine language instructions.
Okay. Would you, for the test, would you give us what, like, would you give
Yes, obviously, you don't have to memorize the instruction set with all the codes. Yeah, no, you obviously don't have to.
That would be the whole test.
But as for converting hexadecimal by yourself, you'd probably leave us to that.
Yes,
That converter is so nice.
I know.
yeah, you're right, the converter. You won't have the converter either. So you need to know how to convert between binary and hexadecimal.
But we can have a calculator, right?
Well,
I mean, if you're doing like 16 to the third times something, and you calculate.
Oh, I wouldn't. Well, I don't think you'll need a calculator. Okay, any more questions? Oh, it's snack time, I see.
Well, fine.
Okay, any more questions about the homework? All right, now at the end of class last time, we did a, what I think was a nifty little demo where we had a program that modified itself. Do you remember? Here in figure 4.36 is a listing of the machine language program, and it output 2 instead of, what was the original program? The original program was to take the 5 and 3 and add them and get 8, right? But then what did this machine language program do? What did those first 2 instructions do? Do you remember when we did the demo at the end of class last time?
They changed the adding to subtract.
Yeah, they actually changed the add instruction to subtract, and because this is a von Neumann machine, what's the von Neumann design principle?
Fetch.
The cycle. Okay, so the von Neumann cycle is what?
Fetch.
Decode, increment, execute,
repeat.
repeat. So that's the von Neumann cycle. And what is the von Neumann? In order for that cycle to work, the computers are based on a certain von Neumann design principle. And what is that design?
Memory and instructions
share the same what?
Memory.
And so whenever we do, and why is that related to the von Neumann cycle? Because when you fetch, what are you fetching?
the instruction.
An instruction, and where are you fetching it from?
Memory.
Memory.
And then those instructions work with the data that is also.
That is also in memory. And you see the way, typically the way we put it is we put the data, below the instructions. All right, and because memory stores both the instructions as well as the data, what does that mean we can do? Not only can we manipulate the data, what else can we manipulate? What does this program manipulate?
The instruction.
Yeah, this program can actually manipulate instructions. Now, look, if you wanted to subtract 5 and 3, you obviously wouldn't do load byte accumulator store and then change. You obviously wouldn't put the add instruction in there and then have the program change it to a. You'd just do what in the first place? You'd just put the subtract instruction in there. So what kind of, can you think of any earthly purpose that a program like this that could change another program would do? I mean, what on earth? Why would you ever want a program to be able to do that?
If like conditions change, maybe?
What kind of conditions?
I feel like this might be related to being able to change a program without recompiling it.
Oh, well, maybe, yeah, maybe. No, there's one really, really, really big application that you guys are all intimately familiar with that happens, that is as a result of this von Neumann design where a program can change a program. Can you think of it? When I say it, you'll say, oh,
So is it
yeah. No, not
No,
plugins, not plugins.
Can we have a hint?
Come on, just guess for another few seconds.
Oh,
What program? What kind of program changes people's programs?
like new?
Virus.
Viruses. This whole thing is responsible for. I mean, this whole design principle. That's how viruses work. Because what is when a virus infects your computer? What's it doing? It's changing, it's maliciously changing the programs that are executing on your computer. Are you with me? So this is the heart, the von Neumann design principle and this von Neumann cycle, the fact that we have this von Neumann cycle, this is the heart. This is the reason why viruses are even possible in the first place. Yeah, computer viruses. Because a virus is a program that gets executed on your computer on the sly, right? They trick you. What the virus developers do is they trick you on running their programs, and then what do their programs do? Their programs go in and they change a crucial instruction in your machine that branches to their malicious program, and they do it by changing the instruction a valid, an existing instruction that if it were not modified would execute correctly, and they change that so that when the von Neumann cycle gets to that instruction and it fetches it, but that instruction has been modified, and then what that instruction does is that instruction jumps to their malicious program, and then their program takes over, and then it goes back, and it covers up its trail. It goes back, and so it makes it look like it never did execute, but in the background it did, and so it's doing all of this malicious stuff in the meantime. You never know it. But the only reason that works is by this von Neumann design principle, that data and instructions both share memory, and because look. The computer, the memory of the computer, it doesn't have any history. It doesn't know what it was before it got changed. It just remembers, what it is. And that the store instruction, if you store to where an instruction is and modify the instruction, when the von Neumann cycle gets to that part and fetches it, it just fetch, increment, decode, and when it decodes it according to what it is, even if it's been modified. It doesn't know. There's no intelligence in the von Neumann cycle. It's just one endless loop, but it's very, very fast loop. Billions per second. Okay, now so that's the basis for computer viruses. Now, Next thing I want to do is to finish up this chapter is to show you how the components of main memory how memory is organized. Okay, so every computer system has memory organized a certain way. In other words, certain sections of memory are reserved to do certain functions. And here is the, in figure 4.37, is a figure of how the main memory of the PEP-8 computer is divided. So when we did the demo and we executed the load option, do you remember where did the program get stored? Starting at what address? Yeah, at the very beginning at 0000. Okay, so in this schematic here, we're showing mem is an abbreviation for memory, obviously, and that 0000, that's where the first instruction of the program is going to be loaded when it gets loaded into memory. So that's the region for the application program. Now, and do you remember how many bytes there are in PEP-8 memory? 64,000, 64K. So the address of the last byte is what? FFFF. Okay, so what we have here is the byte addresses from 000 to FFFF, and the top part of memory, we'll call it the top being the low address part, okay, is where the application program is, and then the operating system is at the bottom. Now, what level is the operating system?
5.
I think 4.
How does it go?
6.
It's OS 4, right? What are the levels? Top one? 7.
Our language.
No, 7 is application. 7 is application. HOL 6.
Assembly.
Assembly 5.
Operating system.
OS 4. And then ISA 3. And then, remember the other ones?
Microcode.
Microcode
Logic gate.
2 and Logic Gate 1. Okay, so the operating system is that fourth level. It's between what two levels? The assembly level, you have the operating system, you got machine level. Okay, so the operating system is a program, and PEP-8 has an operating system. And in fact, if you're interested in looking at it, you can check out, I forget what chapter it's in. But there's actually an operating, I think it's in chapter 8. The operating system is all described in chapter 8. And the operating system is a program that resides in the bottom part of memory. So here it's FBCE is the last byte available for the application program, and FBCF is the first byte of the operating system, and the operating system goes all the way from FBCF to FFFF. Okay? So this is called a memory map, all right? A description of which parts of memory are reserved to do what functions. Now, are you guys familiar with ROM? You know what ROM means? Yeah, ROM stands for read-only memory. Now, unfortunately, ROM is not a good acronym, because basically there are two kinds of chips that you can plug in to a circuit board. One is called random access memory. That's known as RAM, which is RAM. So like when you install memory in your computer, you have this chip, and it's a RAM chip, and those chips get plugged into the circuit board, and the circuit board plugs in. And so that's RAM, that's random access memory. And so the abbreviation is RAM. Okay, so I take it back. ROM is not the bad acronym. RAM is the bad acronym. Now, do you remember what the load instruction does? Mm-hmm. It takes information from where to where?
From memory.
From memory to the
Selected register.
in the
CPU.
So it goes from it. So load goes from memory to the CPU, right? And now, in the programs that we executed, that we have demoed, the store takes memory from information from where?
The CPU.
CPU to memory. So when it goes to memory, the original content in the memory was wiped out and it was replaced with what got stored there. Are you with me? So unspoken in all of that is that those memory locations that we use to store that data was RAM, random access memory. But it shouldn't really be called RAM. What it should be called is here. RAM should be called RWM. In other words, read, and RWM stands for read-write memory. So the read, so check this out, you guys. This is not a good pen. Whoops.
Airball.
Say airball. So this is read, and this is write. And reading is what you do when you do a load. And write is what you do when you do a store. So what you do is you read from memory and you store to memory. You see what I mean? And whenever we had those programs that did loading and storing, loading we were reading from memory, and storing we were writing to memory. And that RAM chip was able to do both. And whenever you write to a RAM chip, what you're doing is it's writable. That RAM is actually a read-write memory. And now, what's the acronym ROM?
Read only.
Yeah, ROM is read-only. Now, what do we mean by read-only? Read-only means you can do what?
Load.
You can load from a ROM chip. And what do you suppose happens when you store to a ROM chip? Well, the machine continues to, nothing stops. In other words, if you actually store to ROM, the computer will just keep going on. But what happens is the original content does not change.
Okay.
You see what I mean? It's like it's permanently burned in.
It's like CD-ROMs.
Yeah, like a CD-ROM. That's why they call it ROM. Yeah, read-only memory. Yeah. Is everybody clear on that? So it's not that anything bad happens. You don't hurt the machine, you don't hurt the circuitry or anything like that. But if you store to read-only memory, that content doesn't get changed. Well, wait a minute. If you can't change the content, then how does the original content get put in there in the first place? You see what I'm saying? If you don't, are you with me? If you can't write to it, then how did it get its? It's wired in. That's right. The bit pattern is actually wired in. And with some chips, you see what I'm saying? So it's like burning a CD-ROM. You burn it once, and then you can just read from it forever. And when the power goes down, guess what? When you turn the power back up, it's still there. That bit pattern is still there. So it doesn't even get erased when you turn the power off. Are you with me? So what happens is, if you have a ROM chip, the ROM chip inside your computer is a little part of memory that has the bit pattern permanently wired in, and that's part of the design of the chip. So, like if a computer manufacturer wants to buy a ROM chip from a ROM manufacturer, the ROM manufacturer says, okay, well, what pattern do you want? He gives them the pattern, he gives them the chip with that pattern burned in. All right? Does everybody see how that works? Okay, now, so read-write memory is also called random access, and read-only memory is called ROM. But here's the problem. The problem is that ROM is random access.
Oh.
Now, you see what I mean? Now, what do we mean by random access?
You're able to go to any point in the
Yeah, it's not like a disk where you have to wait for it, It's not like a disk where you remember those 3 times for accessing data on a disk? What's the first one?
I think what it does.
What's the first time? There are 3 times that have to elapse to read.
to get to
To the right.
The needle.
Yeah, the head has to get to, what time is that called?
Seek time?
Good. That's the seek time, the time it takes the head to get to the track, and then what's the next time?
The disc has to spin.
It's to spin, and what time is that called? It has to spin to get to the under the head. Somebody said it already.
Transfer?
No,
It's late.
it's latency. That's the latency,
That's
okay? And then, once the head is there, and the track, and it's on the right, and the sector is there,
So it can move over.
it has to actually get in under the head. That's the transmission time. Okay? But notice that is inherently that's not a random, okay? That's not a random device. That's a sequential. In other words, you have to wait for it to, Also, do you guys ever even see tape? I mean, were you around when
Yes.
when CDs? I mean, when
VHS and cassette tapes?
VHS?
VHS? Oh, you were around with VHS? Okay.
We had like
All my
100
Disney
VHS.
You had 100 VHSs in your collection, and now they're all. Yeah. What happened to them all?
We had a big
Give away.
VHS camcorder.
Oh, you had a VHS
yeah.
camera? Well, that's obviously not a random access, right? Because if you wanted to go to a certain part of the film, you had to, it was a sequential access.
Disc?
No, disc is
Those
Gesundheit.
were random access, but neither are like DVDs.
Neither are DVDs. But chips are random access. In other words, if you want to go to memory location, FF5D, you can just go right to FF5D, boom. You don't have to wait for FF50, FF51, FF52, you don't have to wait for it. You just, boom, go right there. But the thing is, both RAM and ROM are random. So it doesn't make sense to call this random access as opposed to ROM,
Right.
because, ROM is RAM. I mean, it's not, it's not, it's a bad acronym. It's not RAM, but ROM is random. ROM is a random access memory.
They came up
But for
with one of them
CD-ROMs,
before the
it's
other one.
appropriate.
For CD-ROMs, it's appropriate. Okay, so now this next figure 4.38, shows how the operating system is divided into two parts. Okay, and the bottom part of the operating system is the operating system ROM, and that starts at memory location FC57, and it goes to FFFF. Okay, so there's a little tiny small chunk of the operating system that's burned into ROM, and that's at the very bottom of memory. Okay, and then there's operating system RAM, which starts at FBCF and goes down to FC56. Are you with me? And then the application program is all in RAM. So you see RAM, the dividing line between RAM and ROM is not the dividing part between the application and the operating system. You see what I'm saying? The application is all in RAM, and then there is a RAM part of the operating system, but then there is a ROM part of the operating system as well. So the operating system, most of it is burned into ROM.
But some of
The
it-
PEP8 operating
it has
system,
some
most of it.
writable areas.
Yes, it does have a small little, in fact, you should be able to count how many bytes.
Oh, okay.
FBCF to FC56.
It's not many.
That's not many.
56.
56, 57, 58, 59, 5A, 5B, 5C, 5D, whatever. Okay, but anyway, it's not very much. I think it's just like 100 or something like that. 120, I don't know. So anyway, but anyway, it's relatively small. Most of it is the operating system ROM. Okay, so now what's abstraction?
Adding detail.
So here's even more detail. All right. So now here is the specific most level of detail that we're going to look at the moment of the memory, how the memory is partitioned. Okay, now this is called, did I mention before, this is called a memory map? Okay, this is called a memory map. It's the diagram of which parts of memory are reserved for what parts. Okay, and so let's just take a look at this memory map. First of all, let's review. What is the C++ memory model?
Input? No.
No.
No,
Oh,
That's what a program does. What does a program do?
And
Takes input,
CPU?
No. It processes it and
No.
produces output. Input processing it. That's what a program does. By the way, that's what a circuit does too.
C++ memory.
But what is the C++ memory model? Memory model.
I remember. That's like the heat is.
Yeah, that wasn't the first one. Remember what the first one was?
Oh,
But I don't.
The C++ memory model.
Wow.
This is where, oh.
it wasn't parameters.
No, that's what happens when you call a function.
Local objects are
What?
or like
Oh, you're close. Yeah. What's the first one? What was the first one?
Global variable.
Okay, first of all, global variables are stored where?
Location.
In a fixed location in memory.
Local variables.
Local variables
Runtime
No,
stack.
runtime stack.
on the runtime stack
And dynamically allocated.
dynamically are stored where?
Heat.
On the heap. Okay, so now,
There we go.
let's take a look.
Second day.
Let's take a look now at figure 4.39.
Was that this semester?
Was that, seems like a long time ago. It seems like last year.
It's on my second pages of notes.
Okay, so check this out. Now, I actually didn't show it, but the two of those three locations in memory are shown here. Do you see there's the user stack and the heap? So now that user stack, that's where what is stored?
Local variables.
Local variables. Actually, there's one other category.
Parameters?
Parameters, yeah, local variables and parameters, and the return address and the return value, you know. Okay, so you see, and where does that user stack start? It starts at FB, well, the top of the system stack is FBCF, so it's one less than that. So the top byte on the user stack would be at FBCE. Are you with me? Like if you push a byte, when you push a byte onto the user stack, that's where it's going to
Would it be
go.
counting downwards as it went higher on the stack?
Well, notice that the addressing starts at 0000, and we count as we go down in memory.
Yeah.
We count like this. So the stack grows this way. So in order to push something onto the stack, what do you have to do to the stack pointer?
Never mind.
Do you add it? Do you add to it, or do you subtract?
Subtract.
You subtract. All right. Does everybody see that that's how the runtime stack is going to grow? And it starts at that point in memory. And then the heap is whenever you get your program all set up and loaded, the heap starts right after the last part of your program. Are you with me? Now, so that's where dynamically allocated variables get allocated. Now, what's the other area that doesn't appear up here?
Fixed memory.
Yeah, fixed location in memory. Now, where do you suppose those fixed locations in memory are?
In between the heap and the stack?
No, they're not, actually. They're not in between the heap and the stack. They're not on the heap and they're not on the stack. The only place left is where?
The operating system.
No, they're not.
program.
Yeah, they're actually mixed in with
Oh, okay.
those fixed locations in memory. They're actually kind of mixed into that in that application program. But they're fixed.
Which one of these have we been using with our Pepe program?
Fixed. Yeah, we've been using fixed. In fact, you know how we had the 3 and the 5? Remember how we did da-da-da-da-da, and then we did 3, and then we did 5, and then we had, well, see, those were fixed locations in memory, so those are in that application program block up there.
Okay. Are we going to be able to, in machine code, pull from the stack or from
Oh, yeah, we're going to do a lot. We're going to do a lot. And we're also even going to do the heap. Yeah, we're going to do new. Yeah, we're going to see how all that works. That's why we want to understand the memory model, the C++ memory model.
Is there actually, so there's no difference between like the memory and the heap, the memory and the stack, other than where they're placed in the memory index?
That's right. They're all in RAM. But what happens is the operating system, that's the reason, in order for the operating system to work, the operating system has to manage what goes where in memory, and it has to keep track of where everything is. The operating system is a program that does that, and what I'm describing here is the areas of memory that are organized by the PEP8 operating system. Now, it's a little unrealistic because in a real system, the programs, first of all, there can be more than one program in memory at once, so they obviously can't always start at 0000. Are you with me? And so this is a big simplification, but the operating system has to manage what you know, what is in memory and where the, and you know, and there's a stack for, if there's like, you know, 10 different jobs in memory at once, then each job has its own little stack. So it has to keep where, you know, keep track of where the stacks are. Yeah, yeah.
Is that true for the heap as well?
Yeah, it is. It is. And then, okay, and then from at FC4F, okay, so that's the input-output buffer. That's what the operating system needs, that little input-output buffer. And then just the one just above FC4F, which would be what? FC4E. That is the first byte that goes on when the operating system needs to use a runtime stack. Its runtime stack. It has a reserved place in memory for its own stack. Okay, so FC4E would be the first byte allocated for the operating system. Are you with me? And we'll see where that will. I'm not sure if we'll get into much of the details about that or not. But now, and then starting at FC4F, that is the input-output buffer. That FC4F is the smallest byte. That's the address of the first byte of the I/O buffer. So how many bytes are in the I/O buffer? From FC what? 5. 5. Wait. How do we count that? 4F. Okay, so it's 4F.
50.
50.
51.
51, 52, 53, 54, 55, and 56. Because 57 is the first byte of the loader.
So 7.
So there's 8.
Oh, 8.
So there's 8 bytes in the I/O buffer. Does everybody see how to count that? Are you with me?
Yes.
You look a little puzzled here? Are you off by 1?
No, it is.
Because see, FC4F is the lowest.
And then 0.
Is the lowest address, is the smallest address, the top address of the I/O buffer. FC57 is the top address of the loader. So 57. So then it would be the bytes, the addresses of the bytes in the buffer would be FC5, 8, 9, A, B, C, D, E, F. 8. Okay, so there's 8 bytes in the I/O buffer. And then this loader is the part of the operating system that actually takes your program and from the input device and loads it into memory. Now, do you remember when we selected the load option when we did the demo? And when you write a program, what do? You have to do load, and do you show the memory thing and see it loading? And so the loader is the program that does that. And that's a common function of an operating system. The operating system what the operating system does is it has all of these jobs, they're all on the hard drive. And in order for it to be executed, one of the things the operating system has to do is it has to get the program from the hard drive and put it into memory. That's called loading, okay? It's complicated. It's a lot more complicated than this. They have linking it because it has to set up the library. You know, like if you have a program that uses a library, it has to make sure that the library is in there and that when this thing makes a library call, so it has to put all that stuff in there and get it all coordinated so everything works together. Okay, so that's the loader. Very common. Every operating system has to have a load system. Okay, and then starting at byte FC9B is what's called the trap handler. Now, do you remember the word trap? Where have we run across trap before? Does that sound familiar?
Nope.
Doesn't sound familiar? Whenever we looked at, here, let's go back. Oops, here it was.
Oh, yes.
Does this look familiar? Figure 4.6? Remember how this worked? What is this? What is the instruction at 00100001R? Which one is that?
Rotate right?
That's the rotate right instruction. But what's the one at 001001NN? That is a what? Unary trap. Okay? So there is this group of instructions here that we never did explain before. They are called trap instructions. So what happens is if you have a machine language program that has the opcode 00110 AAA, if you have a machine language instruction that has that bit pattern in there, what happens is that that's a trap instruction. So to go back to this memory map, oops. So to go back to this memory map, what happens is when that opcode executes, it jumps down to the trap handler in the operating system. And the operating system takes over, and it does, it's kind of like a function call. But it's an automatic function call in the hardware that goes to the, and then the operating system provides a service. Do you see what I mean?
What's the service?
Well, we'll see. And actually, we might see this hour. We might see pretty soon. Actually, I think I'm sure we will. Yeah, you don't have to wait too long. All right. But before we go to the next chapter, now here's a crucial little part of another crucial little part of memory. Look at, now there's 4 words. Now, how many bytes are in a word?
8. 2.
2. 2 bytes in a word, okay? And these last 4 words, they are at address FFF8, FFFA, FFFC, and FFFE. Are you with me? And this is this burned into ROM or is it in RAM?
ROM.
This is burned into ROM. And look, you guys, do you see why there's 2 bytes per by looking at the addresses?
Yeah.
Okay. And what is the content of FFF8?
Is it an address?
It's FBCF. And does that look familiar?
System stack.
It's the first part of the
Yeah.
operating system.
Yeah. It's FBCF what did you say? It's the
System stack.
Address.
it's actually the bottom part of the user stack.
True.
Are you with me?
Oh, okay.
So that's used for yeah. So whenever the runtime stack starts to kick in, it has to start somewhere, and it starts. So you know the stack pointer is not pointing to the. It's always pointing to. It's not pointing to where the next byte is going to be pushed. It has to be subtracted, and then the value gets pushed on. Do you see what I mean? Okay.
So that actually is the default byte or stack point.
It's the default, well, it's the starting value of the user stack. All right? And now what's at FFFA?
FC4F.
FC4F. Now what's at FC4F?
Input output.
Oh, that's the input output buffer.
Or it's where the
bottom of
system stack.
Oh, wait a minute, you're right. That is the start of the system stack. Okay?
Isn't that still in the IO buffer?
Well, as we did before,
Yes.
So just
the question is, do you subtract 1 and then store, or do you store and then subtract 1?
Subtract.
You subtract 1 and then store, or you subtract 2 and store a whole word. Are you with me? That's why it's actually the bottom of the system stack. And now what's that FFFC? What's that FFFC?
FC57.
But now what is FC57?
The loader. No.
No. This is not a stack. FC57 is what?
The loader.
It is the first byte of the loader. Now, what is the loader?
Wait, how come on that one we didn't go up? Or-
Because it's not going to be subtracted and pushed onto a stack.
But the other ones were.
Yeah, because they were at the bottom of those stacks.
Because that,
Are you with me? Because they were at the bottoms of those stacks. What don't you get? No, FC57 isn't the bottom of a stack.
the IO buffer isn't a stack.
The IO buffer is not a stack.
Okay.
Are you with me on this?
Yeah. It just seems kind of weird to me. Because the other ones, okay, so the FBCF, we went up.
FBCF is, okay, let me put it to you this way. FBCF is the very, very top byte of the system stack, but we initialize the stack pointer to that because it's at the bottom of the user stack.
Because for
And
stack, you subtract. Then.
You subtract and then store. Are you with me? Okay, and so, but FC57, so what is FC57? That's the address of the first instruction of the loader.
Which that's in ROM, isn't it?
It is in ROM. And the loader program, actually the loader is part of the operating system, and if you want, you could actually, the loader, you could actually see the loader itself. It's on page, here, it's on page 382, if you want to see what the loader looks like. Here's a picture of the loader program. Okay, that loader program, so that's the address of the first byte, the address of the first instruction of the loader, and then what's in FFFE?
The address of the trap handler?
Yeah, the address, the first instruction of the trap handler.
Okay, so is the FC4F, that's the bottom of the system stack, not the
FC4F is the bottom of the system stack. FBCF is the bottom of the user stack. FC4F is the bottom of the system stack. FC57 is the first instruction of the loader, and FC9B is the address of the first instruction of the trap handler. Are you with me? So look, you guys, what happens when you go do the load option? You know, remember how in the simulator when you go on the virtual machine, when you do load, guess what happens?
The loader.
Well, here's what happens.
I was wondering what the SP and PC buttons were for.
Yeah, what does SP get? Look, what does SP get?
The memory at...
It goes to mem, what does it say? Mem sub what?
That address.
FFFA. So it goes down to mem FFFA, and what does mem FFFA have in it?
The system stack.
FC4F. So do you see that SP gets FC4F? Are you with me? Then what does it do? It goes to mem sub what? FFFC. Well, let's go down here to what is in mem FFFC?
The loader address.
FC57. So what gets FC57?
Program.
The program counter. So when we start the von Neumann cycle, what happens? It starts at what? What?
It starts with
What?
the loader,
We start the von Neumann cycle. So what does the von Neumann cycle do? Fetch. Where does it fetch?
it fetches from
The
the,
address of the program counter.
But what does the program counter have in it at this point?
The top of the loader?
Yeah. So that means it's going to start executing instructions from the loader.
Okay.
Are you with me? Is everybody clear? So that's how the load option works, right? So here, what happens is, here's a little figure 4.40, shows in detail what happens. FFFA has 7C4F, FFFC has 7C57, and SP gets mem FFFA, so that makes FC4F go into the stack pointer, and then it makes FFFC FFFC57 go into the program counter, and then it starts up. So when it starts executing, what program is it going to execute? The loader program, and that's going to load your program into memory. Are you with me? Now, after you do the load, well, then what do you do?
who's going to go to the trap?
No. After
Only
you,
if there's a trap.
then when you do, after you
Go
do,
down to the...
then what do you do? And after you load, you know, when,
Oh, decode.
well, yeah, it will do fetch, decode, increment, execute, read, but it'll do that over and over again. And as it goes through that endless loop, that's what will get the program loaded into memory. Are you with me? Then there's a stop instruction. Then what do you do? What does the user do after you load it? Then what do you select?
Then you execute it.
You select execute option. Now guess what happens when you select execute option?
The program counter goes to 0.
No. Oh yes it does, you're right, sorry. Yeah, the stack pointer goes to what? mem FFF8. So but what is here, down here? What is in FFF8?
The address of the trap handler.
FBCF, right?
So the bottom of the user stack?
Of the user stack.
The bottom of the user stack. So you see, that goes to the bottom of the user, and PC goes to 0, 0, 0, and you start the von Neumann. But when you start the von Neumann cycle, what is that? What's the first part of the von Neumann cycle?
Fetch.
Fetch. So now where's it going to fetch from?
From
0, which is where your
program.
program starts. Does everybody see how that works? Now here's my question. Why does this SP get, what happens when SP gets mem FFF8? What actually goes to the SP? What actually goes to the SP?
What is at
FBCF.
FF8? So FBCF.
FBCF. Why isn't it this? Why isn't the whole system designed like this? Why isn't it designed like this? SP gets
FBCF.
FBCF.
Instead of going to
FBCF. In other words, why does it go down to FFF8 and that's what it gets? Why isn't this wired in to the hardware?
If you have multiple programs, you might not want it to start there.
It's random
Well, it
access.
won't always start there. It's possible that it could not be FBCF. It could be somewhere else in memory.
What? How? Yeah.
Depending on how the user stack, how much space they take up, everything, the applications.
Yeah, and actually not so much the application, but the what?
Stack.
The heap.
Well, the whole operating
Yeah,
system.
everything, right.
In fact, you have the ability to rewrite to modify the operating system. Are you with me?
Yeah.
Everything above the ROM part, right?
Everything.
No, even the RAM part. Yeah, even the ROM part. You can modify the ROM with this app.
Oh.
You can actually modify ROM. You can burn it. You can burn it in.
Isn't that by definition wrong?
Just
No. Well, it's like it's like going to the manufacturer and say, I want this ROM. Boom. You can actually do that with the program. All right. So what happens? Because look, what's so special about FBCF? It might be different. If the operating system is a little bit bigger, then you might want the SP to start at a little bit lower value,
Right.
or you might want to start at a little bit higher value. So what number would you pick here? Once you committed to this number, it would be
If that was Yeah.
inflexible. I mean, you could never change the operating system. But on the other hand, if we store it down here, then if we change how big the operating system is all we have to do is change what?
the address.
Is change what address is stored there. Yeah. So that's called a machine vector. Okay, the bottom 4 words are called machine vectors. And the reason they are there is for flexibility. Okay, so that you can change how big the operating system is and have the stack start wherever you want. So all you'd have to do would be just, because no matter how big you change everything else, what do you know about these last locations? They're just fixed, you know, they can just remain fixed. And so all I have to do is burn in another value. Okay, does everybody see how that works? Okay, now I'm sorry that I lied to you, because we are not going to be able to start chapter 5 today. But suspense, previews of coming attractions. Next chapter we will see how what those trap instructions do. And I promise you, you're going to like it. You're going to like what we do.
You promise?
I promise.
Something earlier today.
Yeah, I know. Okay, I'll see you next time.